Boy, I'll tell you, they really love the mass on a spring problems on the AP Physics exam. So we need to be sure that we know all the different variations of these. The two main ones that we're going to look at are a mass on a spring vibrating horizontally and one vibrating vertically, hanging from a spring. Now, in terms of the equations for period and frequency and force, those don't depend on orientation, so those are all going to be the same for each one of these situations. What will be a little different is on a problem like this, the horizontal ones, they're going to have to give you some information to help you figure out how far that spring gets stretched and compressed, and they definitely have to give you a value for K. On the vertical situation, they might say something like a mass is hung from a spring and it causes it to stretch out by this distance. So then we can figure out, okay, well, if the mass is hanging, then we've got a certain amount of force on the spring. It stretches out this far, so the spring constant then would be this, using the F equals negative kx equation. So let's try one of each of these. We're going to do a vertical one first. And it'll be set up just like I was explaining. So that mass is hung from a vertical spring, and it stretches it a distance of 0.40 meters. So when we think about the mass hanging from the spring, we've got the spring force upward, and we've got weight downward, which is going to be the same as mass times acceleration of gravity. Now these two forces have to be equal to 0 because that object comes to rest. So our spring force minus mass times gravity has to equal 0. So spring force in this case is going to be 2 kilograms times 9.8 meters per second squared, or 19.6 newtons. So now we can say spring force is equal to negative kx. Here our spring force is 19.6 newtons. Equals negative k, and our distance stretches down by by 0.4 meters, so negative 0.4 meters. So then k is going to be equal to 19.6 divided by 0.4, which is 49 newtons per meter. Alright, the mass is then pulled down and released. What's the frequency of oscillations for the mass? So let's first get the period, or I guess we've got frequency listed down already, so 1 over 2 pi times square root of k over m. So frequency will be 1 over 2 pi times the square root of 49 newtons per meter, divided by the mass was 2.0 kilograms. So that gives us a frequency of 1 divided by 2 pi. Be sure to put that 2 pi in parentheses when you type it into your calculator. Times 49 over 2 to the 0.5 power. And we get 0.79 hertz for the frequency of oscillation. For our horizontal problem, one thing they really like to do on these AP tests is combine multiple concepts onto a single problem. So here we're going to have a collision taking place before our object starts to oscillate. So whenever we have a collision, we know right away we need to go to conservation of momentum on this. So once we have that conservation momentum, we can start we can start looking at the spring and the oscillations that are caused by this. So with conservation of momentum, we'll say total momentum initially is equal to total momentum final. So that'll be 3.0 kilograms on the initial side times 4.0 meters per second to the right plus 0 is equal to, and here it says that those two blocks are going to stick together at the end, so we're going to have just one big mass with 5.0 kilograms times the final velocity. So then we'll have 12 kilogram meters per second is equal to 5 kilograms times v. So our velocity is going to be just 2.4 meters per second. So once this one hits the second block, they're going to move together now at 2.4 meters per second to the right. Now we've got the speed for this big block, the 5 kilogram block. At this point, right before our spring gets compressed or stretched out, that's our equilibrium position. So at that moment we have our block moving, but the spring isn't stretched or compressed. That says to me, we're probably going to be dealing with some energy here. So we will use the conservation of energy equation. So initially we're going to have just the motion of the two blocks, 1/2, and I'll switch to a big M for the two masses combined, v squared is equal to, and then at some point later that mass is going to come to a rest, and that'll happen when that spring is as compressed as it can get. So that'd be all spring potential energy. Okay, so the 1/2 on each side, I can multiply both sides by 2 to get rid of those. And then, we'll have our mass, 5 kilograms, times our velocity, 2.4 meters per second, squared is equal to K, and that was given as 75 newtons per meter, times x squared. We'll divide both sides by 75 and then square root, and so we get, let's see, 5 times 2.4 squared divided by 75 and square root. X is 0.62 meters. That's the farthest that spring is going to compress, so that'll be our amplitude, 0.62 meters. The other question was the period of the resulting vibration. So period is equal to 2 pi square root m over k. Nothing tricky here, except got to make sure that for that mass we use 5 kilograms divided by 75 newtons per meter. So our period then is going to be 2 pi times 5 over 75 square rooted, and we get 1.6 seconds.